So the final speaker is Dr. Nigel Moriarty from Lawrence Berkeley National Labs in California. And he's going to be talking about work related to the Phenix software package that he is a developer of.
Okay, so thanks, Jonathan, and thanks for the invitation. And as stated, I'm going to be talking about how I've used MOPAC in molecular refinement. And one of the cool things I should tell you is that Phenix is a large project of several different groups, and we work together to create a software package so that both academia and industry people can refine their proteins or actually macromolecular models so that they can find out what's in their crystal. It's similar to, I'm sure, what the previous speaker has done. I'm a developer, but I also get to use our software in anger because a lot of the users will say that they have an issue and they need a little bit more expertise. So I get involved with the use as well as the development, which is a fairly unique position, I guess. So one of the things I was going to talk about was the implementation of chemistry in silico, so that you know a little bit of background of what is needed in refinement, and specifically ligand restraints can be calculated. And one of the things that's been around for a while is you calculate these restraints in a vacuum, but just this last few months I've developed a method using an in situ method. I'm working on getting energies out of this, which is why I had a previous question. And then some of the other topics that are coming along is histidine is a side chain of the protein, but it changes its protonation and its split based on the pH of the specific area of the protein that it's in. And also metal coordination is a fairly hot topic at the moment. So in protein refinement, X-ray crystallography and cryo-EM, you have to convert the chemistry that you know about a specific entity into parabolic force fields, and that usually means that there's a bond restraint, an angle restraint, and other restraints that try and keep the a priori knowledge of chemistry in the model so that you can compare the computer model of the chemistry with the experimental data that you've gleaned from your experiment. Each of these has an ideal bond length, for instance, in the case of a bond, and an estimated standard deviation, which represents how stiff that restraint is. So, for instance, a sulfur bond is going to be not as stiff as a carbon-carbon bond because of the characteristics of the bond. And these are used to calculate gradients so that you can weight the chemistry against the experiment. To do this, for the longest time, I've used both. If a user has MOPAC installed, they can optionally use MOPAC to calculate good geometries of their ligands, which is the target mostly, because proteins and nucleic acids are fairly well known, so that they don't need to calculate the accurate geometries of that. And with Jimmy's help in 2009, I wrote some C++ code to calculate AM1 and RM1 in Phenix, so that the users were getting that as part of the distribution. However, just recently, I stepped up the use of MOPAC in particular, and it's now being distributed with Phenix in the Python 3 version using the Conda installer that John talked about earlier. So you can download Phenix, and it comes with MOPAC. And This is used, and we just published this, as you can see, at the beginning of this year. It calculates the restraints of a ligand in situ using, by default, the PM63H4 method. So just a quick overview of what that is. If you have a protein with a ligand in it and you want really accurate restraints for this, you want to know more about the chemistry than just in situ, in the vacuum, which is the default way. The code that I wrote calculates, just based on a selection, it creates a ligand with the surrounding protein into a smaller model, for want of a better word, so that you can then calculate the restraints of the ligand just using the smaller model with MOPAC. And so the idea is that you let the ligand optimize in the pocket, but you freeze all of the protein around the outside of it, except, of course, the hydrogens. And I think I cover that in the next slide. Yeah. So all entities near the pocket, including proteins, this is what you need. If there's explicit waters near the pockets, protons are added automatically. You need to have a reasonable idea of what the ligand and pocket conformation is, because it doesn't, as you know, it doesn't do a conformation search by default. So you do this once you've figured out that the electron density is telling you what the protein and the ligand is doing. And then you can do this either just once so that you get the restraints and you can use those restraints further on, or you can do it iteratively so that you're constantly updating the chemistry of your ligand based on the MOPAC geometry density in situ, and then it keeps adjusting for the protein changes. Now, by default, when you choose your entity, and I've chosen caffeine as my example here, just in case people are falling asleep because I'm the last speaker. The orange entities in my model are those things that will be optimized, the position. So by default, it's the ligand, the hydrogens on the water, so that you can see if there's any hydrogen bonding based on the water. And then all the protons on the protein are also done. By default, that's the way it is, but you can also do it if you notice that the side chain is interfering with your ligand geometry. You can optionally let the side chain move as well. And I have seen cases in flexible ligands where if you don't let the side chain move, even if it's just a small amount, the ligand can buckle in a non-physical way, and it doesn't fit the density very well. So this actually is also useful because I do try and calculate energies, and I talked about this in our previous discussion. So you can calculate the strain energy for the ligand in the pocket, and then what it does is it calculates the geometry in the pocket and then takes the ligand out in isolation and then calculates the minima based from that starting point. And the example that I was alluding to before was that if you do this particular ligand, it's known as N72 in the PDB database. If you just do it in the vacuum, the energy difference is 100 kcal. And you can see that Avogadro has drawn in a bunch of hydrogen bonds, and that this was buckling this fairly long chain. If you do it with a solvent model, I just use EPS 70 equals 78. It reduces the number of hydrogen bondings and also changes the energy quite a bit. So that is something that I'm still investigating, because it's not completely straightforward how to evaluate the strain energies. The histidine configuration is based on pH, as I said, but there's 6 different ways that a histidine can be protonated and flipped. 3 protonations and 2 flips makes 6 different conformations. So what my code will do if you want to do it, it selects the histidine and any waters, because it's all done in situ, because you're trying to find out what's the best conformation for this specific histidine. And then the options that I've played with is you can freeze the main chain atoms and just idealize the side chain. You can freeze everything except the ring, which is very interesting, and I call this an unconstrained refinement. And then you can also freeze the dihedral, which is really great in MOPAC. Is that I was just reading the documentation and I was able to figure out how to do all of these things programmatically in my code. And so what that leads to is my algorithm will take the 6 starting configurations of histidine, minimize the atoms that you've chosen, and compare a number of metrics that I have played with. And I'm using this example here. So this is what the each of the histidine configurations looks like. You can see that the water molecules in the background are rotating appropriately to create hydrogen bonds, and depending on the protonation state. So that's a very nice thing as well. And then here is some of the results. The top is the completely relaxed, and the bottom is I've constrained the all the way up to torsion. And you can see that there's fairly big differences in energy here. The smallest differences in the order of 20 to 30 kcals. I also have some code that counts how many hydrogen bonds there are, which in this case, the energy and the hydrogen bond count is comparable. And then if you're familiar with rotamers, I also point out which rotamer each of the configurations is. Sometimes it can be an outlier and not a real rotamer. So that's still ongoing, but it's a very interesting piece of work. I've used this actually. I had a collaborator want something to do, and they have a non-standard ligand, and they wanted to know what the 4 different histidines that were pointing at it, what was the best way for them to be. So I've given them the results, and we're currently trying to decipher, I should say, what is the best answer there. Some other directions I've been playing with is metal coordination. So it's very nice that there's so many different metals that have been parameterized for PM6. And I have asked John questions about this, because I've actually done calculations where this is zinc in particular, but I've had another user, or sorry, collaborator, who is very interested in some nickel ligands that contain nickel in a heme-like ring, and we've been trying to calculate good geometries and try and fit those geometries to the density. So this particular example here of the zinc is a very, very well compared to the actual results. So my outlook is I want to figure out how to do the energies better. And then there's other entities in the macromolecular models that can be interesting. Carbohydrates, fairly straightforward, I would imagine. Non-standard amino acids, it's a similar thing to ligands. It's how does the side chain interact with the other side chains in the protein. Arginines, it's interesting with arginine because it's a charged molecule, but everybody in biochemistry believes that all the hydrogens are perfectly flat in the plane of the guanidinidine. But I've seen in MOPAC that these hydrogens will bend out of plane to form hydrogen bonds. So I'm very interested in exploring that. And the previous speaker spoke about issues like this in that every time I've calculated something with a charged phosphate, the geometries seem to be a bit out of whack. And so I'm very interested to try and investigate why the phosphate geometries just don't seem to be supported by experiment. And then the final slide is, once again, thanking all my collaborators in the Phenix project.
All right, thank you very much. You've actually helped us wrap up the talks on time. That's great. So are there any questions for Nigel? So I have a question about these optimizations of pockets. Now it's such that there's experimental information on heavier atoms and not hydrogen, and also atoms that tend to stay in place. So I think, like, I guess some of the water that's not locked into place is also somewhat invisible. So in these pockets is all the water believed to be accounted for and relatively locked in place? Or can there be instances of like fractional locations and or itinerant water that it gives you, like, leads to uncertainty in some of this type of analysis?
Yeah, so having a water in place, you can't do partial occupancies as you talked about in MOPAC. So currently the code just assumes that it's 100% there. And I find that if you take the water away, sometimes the ligand will just like snake out of the pocket and it just goes into a non-physical place. So I'm asserting to the user that if they've put something other than protons into the model, I'm assuming that they believe they're there. This code, this little module that I just spoke about, doesn't look at the density specifically. So I have to rely on the user saying, okay, this water molecule is here. I see a density blob for it. It's got to be there at least most of the time. So yeah, there's no partial, occupancy.
Okay. Well, yeah, I mean, you'd have to just statistically weight different configurations. Yeah.
I agree, and that's one of the things that my code does. It writes the MOPAC files, and I mean, if the user was smart enough, not smart enough, efficient enough, or knows enough about MOPAC, they could just go into the file, delete the water, and then recalculate and see what happens, and then you could compare the two outputs. I haven't finished writing the documentation, but that's one of the things I was hoping that the user would do. They would say, "Oh, I've got a MOPAC model. This has calculated this density. This geometry. How can I change it to be more specific to my specific case?" And I can imagine that would be one thing they might do, is remove a water molecule and see what happens to the geometry.
Okay. So